Today's Friday.
Okay.
It's too early. Before he was like a evening, like. I know, it's like a breakfast thing. No. They're, it's too early. I'll eat Chick-fil-A.
All right. Good, there's plenty of chalk. And welcome to our study session. I'm happy to just go through all of the exams, but if you have specific questions, I mean, do you want me to just go through the 3 exams?
Yes.
And, okay, so I'm looking at exam 1, question 1. Okay, so we're taking a limit of the square root of x minus 2 over x minus 4. And this is an example of, it turns out this is going to be an example of using L'Hopital's rule. Okay, so the key is the first thing we try for limits is we just try to plug it in. And so if I plug it in, we get the square root of 4 minus 2 over 4 minus 4. The square root of 4 is 2, so on the top I get 0, and the bottom I get 0. Okay. Now the key for L'Hopital's rule is we either need 0 over 0 or infinity over infinity. Okay, so those are what we call indeterminate forms. And in some sense, it's because we can't cancel zeros and we can't cancel infinities. Okay, so you can't cancel zeros and you can't cancel infinities. When I see a 0 over 0 or an infinity over infinity, I get to take a new form of the limit justified by L'Hopital's rule, where we're going to replace the original limit with the new limit, where I'm going to take the fraction I started with and take the derivative of the top. So this is x to the 1/2, its derivative is 1/2 x to the minus 1/2 minus 0 over the derivative of the denominator, which was 1. And then you try it again. You just plug in the numbers again. So I get 1/2 4 to the negative 1/2 divided by 1. 4 to the minus 1/2, that's the square root in the denominator. So this is 1 over 2 times 1 over square root of 4. That's another 1/2. And so we get a value of 1/4. Okay, and so that's the limit that we would get. Now, that's the only example in the for a 0 over 0 infinity, a 0 over 0 problem for L'Hopital's rule. But the second problem is also a L'Hopital's rule problem, but it's not formulated in the original way. So here we're taking a limit as x goes to infinity of x squared e to the minus x, I think. No, e to the minus 2x. Okay, and so again, we're going to do effectively plug it in, but infinity is not really a number, so we're not really plugging it in, but effectively, we might as well say we are. What happens when you square infinity? It's still infinity. And then I have e to the minus, what's 2 times infinity? Infinity, so I have e to the minus infinity. So the next thing that we have to remember is e to the positive infinity is going to be an infinity, but e to a minus infinity is going to be 0. So what do I have? I have an infinity times a 0. Now it's tempting for students to think that somehow that's 0, but this is like canceling. You can never cancel infinities. So this is a new type of indeterminate form, because we would try to cancel them, we can't. So I would like to use L'Hopital's rule, but it's in the wrong form. So I have to rewrite it as a fraction before I can use L'Hopital's rule. So we're going to rewrite it. So this is not a L'Hopital's rule step. We rewrite the limit as a fraction. And in this example, it's easiest to change this negative power to a fraction. So divide by e to the 2x. X squared over e to the 2x. Okay? So the x squared on top, if I plug in my infinity again, on the top I get infinity, on the bottom I get e to the infinity, which we had was infinity. So here I've got an infinity over infinity. So this is where I'm justified in using L'Hopital's rule. All right? So let's clear some space.
So if we use the arrow, that's how you rewrite the limit?
So the arrow is a way of saying I'm plugging it in, but I don't know if it's a real number yet. Okay? And that's why I'm not writing limits at this point, because this would be the value if it worked out. So the equal sign here says this limit and this limit are the same, but the arrows represent I'm trying to plug it in. Okay, so we're going to go from the last line, and now we're going to justify it with L'Hopital's rule. We're taking a limit as x goes to infinity. We get to replace the fraction with a derivative in the top and the derivative in the bottom. So 2x on top, the derivative of e to the 2x is 2e to the 2x. And I try it again. I try to plug it in. On the top, I get an infinity, and on the bottom, I get 2e to the infinity, so I still doing an infinity over an infinity problem. Yes?
This might be a dumb question, but if you put equals in between the two, like the limit and the infinity over 2, would that be wrong? It's like limit of x to infinity 2x over 2e to 2x. If you put, the top part, where you use L'Hopital's rule. If you put after that, if you put equals infinity over 2e to the infinity, so where your arrow is, if you put equals there, is that wrong?
Technically, yes, but I'm not going to mark that off. Okay? Because they're not equal. This should be a number, and technically that's not a number yet. But so anyway, thank you for the question. It was not a dumb question. We're going to keep going. It's still an infinity over infinity, so we're going to do L'Hopital's rule again. So this example was one where you had to use L'Hopital's rule more than once. So the numerator's derivative is 2. The denominator's derivative is 4e to the 2x. And so this time I've got a 2 over an infinity. And so what's a 2 over infinity? That's a 0. Okay, and so this limit actually is 0. Okay, yeah?
What a change to the infinity over the top.
Yes, if it was infinity over 2, the answer would have been infinite. Okay. Yeah, so if the exponential had been on the top and the power had been on the bottom, I would have been left with infinity over 2, and then my answer would have been infinity. You would have to maybe take care of checking the sign, because it could have been minus infinity depending on if there was a negative. Okay. Let's talk about interpretation. This problem didn't ask it, but if you take a limit as x goes to infinity and you get an answer of 0, what does that mean about the graph? What is it, Jonathan? Yeah, this would be a horizontal asymptote. So this problem would have corresponded to having a horizontal asymptote at y equals 0. In fact, this graph looks something like that. So if you were to graph that on a calculator or something, you'd see that it goes to 0. In fact, since graphing calculators are allowed and maybe even strongly suggested for the exam, it's worthwhile when you do these limits to plot the function and just see if it looks like it's getting what you think it says, right? Because you would want it to go to the same value. Okay. So the third question on, so we're doing exam 1, we came a little late. The third question on exam 1 is also a L'Hopital's rule question, but it's even a little further in disguise than this one was. So let me erase this. So I've got, I'm taking a limit of x raised to a power, and the power, I've got a variable in the base and I've got a variable in the power. And so whenever I have that, if there's ever any issue in the exponent, you should probably rewrite it. So let's check what happens if I plug in 1, and notice I get a 1 over 0, which is like an infinity. So it's going to be worth our while to just check in a new form. So what we're going to do is we're going to rewrite this power using exponentials. We're going to use the exponential function. So technically this is a composition. Every time there's a power, we can always rewrite it as e to the logarithm of the base times the exponent, or the exponent times the logarithm of the base. And so what we're going to do is we're going to rewrite this. What we'll be doing is we'll be taking a limit as x goes to 1 of e to the 1 over x minus 1 times the natural log of our base, which was x. Okay. Now the reason that we're going to do this is if I can find the limit of this piece, this is going to be equal to e to the limit of that piece that we wanted. Let's write it as a fraction. Okay. So what we're going to focus on is we're just going to focus on the formula that's in the exponent. Okay, so this is a consequence, if I could spell, of continuity, that my exponential's a continuous function, and we can take advantage of that. So let's go and let's look at that limit of the exponent. So in the power, limit as x goes to 1 of the natural log of x divided by x minus 1. We're going to just start, just like every other limit, we just try to plug it in. So it's the natural log of 1 divided by 1 minus 1, which would be 0 over 0. So what's that? It's an indeterminate form. And so this justifies we can use L'Hopital's rule, because it's a 0 over 0. So we're going to replace a limit with a new limit that we have hope of finding. And we replace the fraction with the derivative of the numerator, so that's 1 over x, divided by the derivative of the denominator, that's 1. And so I just now plug 1 into this new formula, and I get 1. And so the original limit is going to be e to the 1. So this 1 gets plugged in there, and so our answer, let's write it here. The limit as x goes to 1 of x to the 1 over x minus 1 is just the number e. Okay. Yes?
So with problems like these, where it deals with the limit e to some power, you figure out what the limit of the power is and then just plug that back in.
Correct. Correct. So whatever the formula is up here, you find the limit of that formula, and then the answer is going to be e to that limit. Okay. I think that's all the L'Hopital rule problems that were on the exams. I don't remember if there were some on any of the study guides that were especially worth looking at. I mean, there were some other examples. Okay, let's see what's next. Okay, so continuing in exam 1, problem 4, this was looking at a function and finding all of the asymptotes. So in this problem, we have a function so we've got x squared minus 4 over x squared minus x. We're looking for all of the horizontal and vertical asymptotes. Okay. All right. So if I'm looking for horizontal asymptotes, what is it that I'm doing? Yeah, so this is a limit. So horizontal asymptote is a limit as x goes to plus and minus infinity. What is it that corresponds to a vertical asymptote? Yeah, so this is going to be the division by 0. And the reason for that is when I have a number like 1 over 0, this corresponds to either a plus or minus infinity limit, that the function is either going up forever or going down forever. All right, so the horizontal asymptote should be maybe the fastest thing that we could do. We're going to take a limit as x goes to infinity of our function. And so we're taking a limit as x goes to infinity of x squared minus 4 over x squared minus x. And I want to emphasize that the limit structure that we're doing right here for this function is the same as we were doing at the end of the semester with Riemann sums when we took their limits for our integrals, except it was n's going to infinity instead of x's. Okay. So how would we go about doing a limit as x goes to infinity?
Take out the biggest factor, x squared.
Okay, so one strategy is to identify the biggest factor because that's what's going to infinity the fastest. That's, in some sense, control of the dominant behavior. So we're going to factor this out and, in other words, divide every term in the numerator by x squared. We're going to divide everything in the denominator by x squared. Sometimes people think about this as dividing the top and bottom by x squared. That's an equivalent way of thinking about it. So we're going to rewrite this as factoring out x squared. Divide this by x squared, I get 1. Divide 4 by x squared, and that's exactly what I get. Factor out x squared from the bottom. When I divide x squared by x squared, I get 1. When I divide x by x squared, I get 1 over x. And the x squares that I factored out, they canceled. So I get this limit of, let's just rewrite it, 1 minus 4 over x squared over 1 minus 1 over x. Okay. And the reason that this is useful is when I have infinity, the x is going to infinity, this is going to be 1 minus 4 over infinity and 1 minus 1 over infinity, what happens when you have a number divided by infinity? It goes to 0. And so this is going to be a 1 minus 0 over a 1 minus 0. My limit is just the value 1. Okay? And so this is a horizontal asymptote. Y equals 1 as x goes to infinity. Now, I didn't insist that we did this again for minus infinity, and that's because if I change it to minus infinity, nothing actually changes except that one of these terms, this one I think, changed to 1 plus 0 instead of 1 minus 0. So all of these things that are 0 are still 0 either way, and so technically, it's actually both sides. Both sides have the same horizontal asymptote. Okay, so that's our horizontal asymptote. There is another way of doing the limit instead of factoring. Any ideas what that would be? Yeah?
What if the powers are equal to 1?
It's not necessarily that it goes to 1, but it's going to be the ratio of the coefficients of the highest powers. Like if this was 3x squared and 2x squared, it would be 3 halves. And that's because this would be a 3 and that would have been a 2.
So if you use that coefficient way, how would you show that you used it? Like instead of doing all the limit stuff, if you just looked at the power and said, okay, it's 1 because they're equal, should we just do the limit? Like,
so if you factor out the highest power, the leading coefficients are going to be the things that survive, plus zeros. If you're going to directly reference it, you don't want to do all the other work, you need to tell me the highest powers. So what you would do is you would say something like this. You would take just the dominant terms and make a comment, these are the dominant terms. And then you know the answer is 1. Okay? All right. So that's horizontal. Any additional questions on horizontal asymptotes? So let's do the vertical asymptotes. So if I'm looking for where it divides by 0, I need to factor it. And it's actually worthwhile factoring the top as well. So let's see, x squared minus 4 factors, and x squared minus x is going to factor. X is a common factor, so I get x times x minus 1. All right, what about x squared minus 4? You should be pretty good at that one. X plus 2 and x minus 2. Now the reason that we factor it is there's always a possibility that one of the factors in the denominator would have canceled a factor in the numerator. If that happens, it's not a vertical asymptote. It would have been a whole. Okay, so if this was an x minus 1 in the top, and that was an x minus 1, that would have canceled, and I would have had just one vertical asymptote. But here I have 2 factors that don't cancel. And so I have 2 vertical asymptotes. One's at x equals 0, and the other is at x equals 1. So it's really easy to know where they are. There is still a limit that we have to calculate. Okay, so let's see, how would we do the limits? Well, we know that the limits are either plus infinity or minus infinity, because that's what a vertical asymptote is. Either it goes up or it goes down, and so knowing that it has a plus or minus infinity, all I have to do is decide the signs. And the way that we do the signs is we use our factorization, and we're going to take our function, and for every factor, we'll identify where it goes to 0. So -2, +2, 0, and at 1. These were our vertical asymptotes, and the -2 and +2 were where my functions were 0. And it's important that I do both the top and the bottom, because otherwise I might miss where it changes sign. Once I know this point, I just need to decide on each interval, is it positive or negative, and how would I do that? Just try numbers, right? So let's start way on the right. Plug in 3, and remember, we don't have to know if it's the value. All I have to do is positive or negative. So if I plug in 3, I get positive, 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 and positive. So it would have been a positive sign. Something between 1 and 2, like 3/2, positive, that was negative, positive, and positive. So I get 1 negative, that's going to be negative. Now, a shortcut is, as long as you don't have powers on the factors, it's going to change sign every time you cross one point. So it's going to be positive, negative, positive, negative, positive. And the reason for that is each time you cross a point, one of the factors switched sign. And so here I have an even, an odd number, an even number, an odd number, and an even number of negative signs. Okay, so sometimes that's a quick way of doing it. Okay, so now that I have this, I actually know what the graph looks like. I have a vertical asymptote. In fact, let me draw the graph here. So here's 0, here's 1. Between 0 and 1, I'm positive, but I have to have 2 vertical asymptotes. The only way I can be positive with 2 vertical asymptotes is if I go up on both sides. I'm negative on either other side, and so my vertical asymptote has to go down like that. So they go down on the sides. At 2, that's where I cross my axis. And remember from our earlier problem, we knew there's a horizontal asymptote of y equals 1. And so this graph is going to flatten out and look like y equals 1. On the other side, crosses at -2 and then flattens out. Okay. All right, so we know what the graph looks like based on our sign analysis, but the problem is asking us to write down the limits. So let me make some space here. Let's write down our limits that we actually wanted. To answer the question, you didn't need to graph the picture, but if I wanted to emphasize that that's what we're thinking about as we answer the question. So for our vertical asymptotes, these are one-sided limits. And of course, the advantage of saying that I have a function is I don't have to write down the whole formula. I just write down the limit of f of x. On the left goes down to -infinity. The limit on the right goes up to infinity. And for x goes to 1, we have 2 sides. X approaches 1 from the left. On my left, it goes up to infinity. And on the right, we go down to infinity. Okay? And so these are the 4 limits associated with the 2 vertical asymptotes. Are there any questions on the vertical asymptotes? Because they were the numerator, So if I plug in 2, the top is 0, so a fraction with 0 over anything else is going to be 0. Same thing here. So where the numerator goes to 0, that's where the function is 0. Where the denominator is 0, that's going to be a vertical asymptote unless they happen to cancel each other. So if both top and bottom are 0, then something weird's happening. Okay. All right. So that's question 4. Okay. Question 5 is a question about the intermediate value theorem. Okay, so just to review, what is the intermediate value theorem? It's about continuous functions. So it's about functions that are continuous on a closed interval. Okay. And what it tells us is it's a theorem that guarantees that the function f of x is going to pass through all values, guarantees that f of x equals y has a solution for every y between the endpoints. So if I have a function, here's A and here's B, and I've got a function, this is my f of A, and I have another y value, f of B, then every y value between f of A and f of B, there has to be some x value where it's going to solve that height. Okay? Now, the most important application of the intermediate value theorem happens to be guaranteeing that the function is going to be equal to 0. And so anytime you have one side is positive and the other side is negative, since 0 is between every positive, like if you take a positive number and a negative number, 0 has to be between them. Then the intermediate value theorem is going to guarantee that the function has a solution where it's equal to 0. Okay, so let's look at this specific question. Okay, so if I plug in 1, and just to double check, 1 plus 2 is 3, 3 minus 5 is negative 2, so that was right. If I plug in 2, I get 8 plus 4, that's 12, 12 minus 5 is 7. So those are the real values. Okay? And we want to know is it guaranteed that f of x equals 0 has a solution with x in the interval 1 to 2. Okay. Well, that interval comes from the closed interval 1 to 2. So f of x is a polynomial. And polynomials are always continuous. They don't have any issues. They're never divided by 0. There's never anything undefined. And we have a closed interval. Now, it's important to note that the interval that was given in the problem was not closed. It was open. But if you include the endpoints, it is closed. Okay, so that interval is really coming from the closed interval 1 to 2. So we have a continuous function on a closed interval, and f of 1 is negative and f of 2 is positive. 0 is between -2, which is f of 1, and 7, which is f of 2. So I've got a y value between -2 and 7. So f of x equals 0 does have a solution. Where x is in the open interval, because it has to be between 1 and 2. It's not on the edges. It's a point between 1 and 2. Okay, and so we have a solution. Now, that's all I'm looking for, this much. So what are the key things that I'm looking for when using the I should have said by the intermediate value thing. So I'm looking for you to point out that the function is continuous. I'm looking for you to talk about it being a closed interval, emphasizing that the y value is between the endpoints, and that you say your reason is the intermediate value theorem. So that's the sort of thing that I'm looking for. Same type of thing later when we talk about the extreme value theorem. I'm looking for you to talk about the function being continuous, closed interval, so that you can refer to the max and the min. All right, so that's question 5. Are there any extra questions on that one? Question 6. So this question was just about practicing taking more than one derivative. This one I hope we, at this point, think is pretty easy. We start by writing it as a power instead of a fraction. And then we get to take derivatives. The first derivative is going to be 1 plus 3 times -1 x minus 2 to the minus 1 chain rule. And I emphasize the chain rule because if this was 3x minus 2 or something in there, I'd have these chain rule factors that come out that are easily forgotten. But this one didn't have it. So what do we get? We get 1 minus 3 times x. That should have been a minus 2 power. That was a mistake. X minus 2 to the minus 2 power. Okay. Now, this problem's been completely written out, but I'm okay with you doing that arithmetic in your head. When I take this next derivative, I get 0. I'm not going to write it down. Minus 3 times minus 2 is going to be 6. X minus 2 to the minus 3 times 1 that I don't need to write down. So I get 6 times x minus 2 to the minus 3. And the third derivative, I'll get negative 18. X minus 2 to the negative 4. Okay. Any questions? Hopefully that one was. All right, problem 7. We start with a function. We're interested in the behavior, so we're going to be doing where this function is increasing and decreasing. We're going to be looking at concavity. We're going to be looking for extreme values. And inflection points. So that means we're going to need the first and second derivatives. So our first derivative is 8x cubed minus 6x. And which of the information will that tell us about? Critical points and increasing, decreasing. So we're going to be solving for where this equals 0. So let's find out where this equals 0. Common factor 2x. 4x squared minus 3. So 2x equals 0, or 4x squared minus 3 equals 0. So I get critical points. X equals 0. Let's see, I'm going to add 3, divide by 4. Take a square root. I'm going to get x equals plus or minus square root of 3/4, which is plus or minus square root of 3/2. Okay. So those are my critical points, and we're going to use that to interpret the signs of this function f prime. So we have 3 critical points. One's at 0, square root 3 over 2, minus square root 3 over 2. Those are the 3 locations where it's equal to 0, and I need to decide if it's plus or minus. It helps to think about what the function looks like. This is a cubic. So cubics tend to look like this. We have 3 spots where it's 0, so it's going to be, the leading term is positive, so it is going up. When I plug in values, it will be plus, minus, plus, minus. If it was a minus 8x cubed, it would have been upside down, and I would have had those reversed. Okay. All right, so we have our sign analysis. How would I interpret this? This is increasing, decreasing. So we would say f of x is increasing on intervals where it's positive. And so it's going to be the interval negative root 3 over 2 to 0, so from here to here. And then from square root of 3 over 2 forever after, that's where it'll be increasing. It'll be decreasing on the intervals where the derivative was negative, so our f of x is decreasing on intervals minus infinity to minus root 3 over 2. And then from 0 to 3/2, so the interval 0 to root 3 over 2. And so those are the intervals where it's increasing or decreasing. All right. So now we're ready for the concavity. Oh, let's answer part C while we're at it. These 3 points that are critical points, what do they become as far as extreme values or inflection points? Which would it be? These are extreme values. And so x equals negative root 3 over 2. What will that be if I'm decreasing and increasing? This would be a minimum at x equals negative root 3 over 2. X equals 0. This will be a maximum. And at positive root 3 over 2, that'll be another min. Okay. Concavity. Take the second derivative, I get 24x squared minus 6. We want to know where that equals 0. By the way, here's my graph of f prime. What we're doing is we're finding where I'm increasing, decreasing, and increasing on that f prime. So this is where the derivative is increasing. That is where my original function will be concave up. Where the derivative is decreasing, that's where my original function will be concave down. And where it's increasing again, I'll be concave up. So we're going to find concave up because it's increasing, concave down because it's decreasing, and concave up. All right, so 6 is a common factor, 4x squared minus 1. So x squared equals a fourth. X equals plus or minus square root of a fourth. That's plus or minus a half. That means that these points are at x equals minus a half, x equals plus a half. So that's what we've just discovered. That's where it's 0. This new function, the derivative, is a parabola. And so we're going to get positive, negative, positive. Right, if I plug in 0, I get negative 6. If I plug in 1, I get 18. Same for negative 1. So second derivative is positive, negative, positive. And so I know that my original function is concave up on the interval minus infinity to minus a half, and a half infinity, and I'm concave down on the interval between the minus a half to the half, and both of these points are inflection points. Okay. Are there any additional questions on that? Okay. So question 8 is looking for creating a graph. And we're given a bunch of information. Let's see, we have a sign for f prime. So our derivative is going to be 0 at 1, and it's something weird's happening at negative 1, and the signs are plus, plus, minus. And our second derivative, negative 1, if the derivative is not defined, the second derivative can't be defined either. Let's see, and 2 is the other point. Plus, minus, plus. Okay. And then we have some limits. So we also know the limit as x goes to minus 1 from the left of my function is plus infinity. How would I interpret a limit like that? X is approaching a number from one side and the limit is infinite. So what's that called? If I get close to -1 as X gets close to -1, the function goes to infinity. This is a vertical asymptote. So that's what's going on here. There's a vertical asymptote. So this is interpreted as a vertical asymptote. Notice the other side is also X approaches -1 from the right is minus infinity. So these together tell me there's a vertical asymptote at X equals -1. So let's make some space here for our graph. Here's -1. And we're going up to infinity on one side and down to infinity on the other side. We'll figure out the rest in a minute. We have the limit as X goes to minus infinity is minus infinity. So what does that say? To say that as X goes to minus infinity, Y goes to minus infinity. That this part of the graph has to keep going down. Before I do much more, maybe I should figure out the shape of the graph. First derivative positive, second derivative positive. What should that look like?
Concave up, increasing.
This says I'm increasing and I'm concave up. And so this part of the graph should look like this, and that's exactly what we want. But it continues to go down forever. Okay. Let's see, one more limit. X goes to infinity, f of x, the limit is 0. What does that say? This is a horizontal asymptote. Y equals 0. So this graph is going to eventually flatten out. So let's figure out some more shapes. This is going to be increasing and decreasing. This is concave up. This is concave down. Decreasing concave up has to look like that, which is consistent with the horizontal asymptote. And so it's going to be doing something like that. What do we have? We've got something at 1, something at 2. So what's happening at 1 and what's happening at 2? At 1, we have a maximum, so let's put it up high enough that our graph is going to go up to it. And at 2, what's happening? An inflection point. So I'm going from concave up, maybe that's not the right spot, to concave down, maximum, and then down. So I have a maximum at x equals 1. I have an inflection point at x equals 2. I've got a vertical asymptote at x equals -1. I've got a horizontal asymptote at y equals 1. 0, y equals 0, I should say. Okay. Okay. So that finishes exam 1. Should have brought a water bottle or something. Okay. So let's talk about exam 2. Okay, so we start exam 2 questions with some true-false type questions. 1A, we have the following information. We have a graph. y equals f of x. We have f double prime at c should have said greater than 0. And the claim is the point at x equals c is a local minimum. Okay? All right. So what does this tell me? I've got a function and it's concave up at a point. Now, is that enough to guarantee that the point is a local maximum? No, but could it guarantee that it's a maximum? It could if there was one more piece of information. So this is going to be sometimes true. It would be guaranteed if we had started by knowing that I was at a critical point. Okay, and that's because this is everything that's required for the second derivative test. And so there was we had a collection of theorems, and the second derivative test says if a function has the first derivative equals 0 and the second derivative is positive, that guaranteed I'm a local minimum. Okay, this piece was missing. So to study for this kind of question, you need to be sure you understand all of the hypotheses for the important theorems that we had. Okay, the second question, part B, says a continuous function will have a maximum value. Okay. So is that always true? No, it's not always true because like a parabola goes forever up. It doesn't have a maximum value. But are there continuous functions for which we do know that there's a maximum value? If we're restricted to a closed interval. So this is sometimes true and it's guaranteed if we restrict to a closed interval. So what theorem was that that lets me know that if I have a closed interval continuous function? That's the extreme value theorem.
And then if you have the parabola, that your endpoint would be your max.
Right, so if I had this on a closed interval, then I'd have to stop on both sides somewhere. And one side or the other will be higher, unless they're the same height, then they're both the maximum value. Yes?
There was one rule that I remember we learned about in class on that where it's like sometimes the endpoints can't be the max.
Okay, so in this same section that the test covered, when it was a continuous function, we were guaranteed it had extreme values. But if it's an open interval, then I don't reach the endpoints, and now I don't actually reach the maximum value. And so what I would do is, if I was trying to find the maximum value, which is what we do on problem 2, I would have to test the limits, and if the value at the endpoint is the biggest value, it didn't actually reach its maximum. Okay, so let's see, part C. see, a function has a maximum at x equals 2 and a tangent line at that point is y equals x plus 1. Okay. Now, when I see tangent line, you should always think slope. The tangent line slope has to match the slope of the function. And so what's the slope of my tangent line? Mx plus b form, it's 1x plus 1. So my slope is 1. That means that f prime at 2 equals 1. So can I have a maximum? Can we have a maximum if f prime of 2 equals 1? No. Because Fermat has a theorem that says f prime of c has to equal 0 or does not exist at extreme values. And so this is never true. Okay, so question 2 from the exam was we had a function. The formula for it, we wanted to find the extreme values. Okay. And so what does that involve? We need to find all the critical points, so our steps. We need to find f prime of x equals 0. And then we need to compare the y values at the critical values or the critical points and the endpoints. Now the thing about the endpoints is it's an open interval, so these are not actually reached. They're going to be holes at those points. Okay, so we start by taking the derivative. Let's see what we get. A fourth, x to the fourth has the derivative of x cubed. A third x cubed has the derivative of minus x squared. Minus 3x squared has the derivative of minus 6x. So I factor an x out, x squared minus x minus 6. That's x times x minus 3 plus 2. So x minus 3 times x plus 2. So I have 3 critical points. My critical points are x equals 0, x equals 3, and x equals minus 2. My endpoints are x equals negative 3 and x equals 4. So how do I check the y values? I just plug all those things into the function f. Okay. Now this is probably going to slow us down a little bit if I do this all. F of 0 is going to be 0. f of 3, I can't remember what the numbers were. Is what? That's going to be at -3. That wasn't at 3. Do you have the solution there? See, I get 81/4 minus 9 minus 27. It was what? Can I just see it?
Yeah.
Oh, okay. I was just remembering wrong. So this is -15.75. It's -5 1/3. So those are the values of our critical points. The endpoints aren't actually included, so technically I'm not really plugging them in. I'm taking the limit. The limit of our function as x goes to -3, and that will be 2 1/4. And the limit as x goes to 4 is -5 1/3. So I looked through my list, and this is the lowest, and this is the highest. The only problem is that I didn't actually reach this. Right? That should have been the maximum, but it's not reached. So my minimum value is -15.75, but there's no maximum value because it gets bigger and bigger. It gets closer and closer and closer to 2 1/4, but it never reaches it. So there is no maximum value. This is the upper bound, but not the maximum value. Okay. So problem 3 was about fixed points and stability. Remember, to find fixed points, we're solving f of x equals x. And once I find fixed points, the stability is based on if f prime at that point has an absolute value less than 1, that means it's stable. And if the slope absolute value is greater than 1, that meant that it's unstable. Okay. So for this problem, f of x equals 13x over x squared plus 4. If we're looking for fixed points, we say when is that equal to x? In other words, when's the output equal to the input? That's what a fixed point represents. So as I'm solving this, I need to cross multiply. So 13x is x squared plus 4 times x. So that's x cubed plus 4x. Subtract 13x over, and I get 0 equals x cubed minus 9x. That's x times x squared minus 9. So there are 3 solutions, x equals 0, and then x equals 3 and minus 3. So those are my 3 fixed points. So I need to calculate f prime. So what rule should I use? Quotient rule. Low d high minus high d low over low low. Something to remind you of how to do that. So low d high minus high d low over low low. 13x squared plus 52 minus 26x squared. So I end up at 52 minus 13x squared over x squared plus 4 all squared. So this is the formula for the derivative. And I'm going to plug those three numbers into this formula. So when I plug in f prime and calculate at 0, I get 52 minus 0, so that's 52, divided by 0 plus 4, so that's 4 squared, 52 over 16. So this point, f prime of 0, has an absolute value that's greater than 1. What does that tell me? That tells me that x star equals 0 is unstable. If I created a sequence with that function close to 0, it would move away from that value. If I plug in 3, I get, let's see, 3 squared is 9, 13 times 9. 115. $63. Over, that's negative 63 over 13,169. I think that's the value. And that fraction has absolute value less than 1. Is that the wrong number?
It's negative 65.
Negative 65. So I get for doing it in my head again. Negative 65. And so the absolute value of that slope is less than 1. What does that mean? That x star equals 3 is stable. Now, x star equals negative 3 has exactly the same value because every x is squared. And so x star equals negative 3 is the same. It's also stable. Okay? All right. So here we had a price for an item was 10,000 over 200 plus x. It depended on the number of items sold, which was x. We want to calculate the profit. And so in general, profit equals revenue minus cost. And so our revenue is the price times the number of items. And our cost is going to be our item cost times the number of items. Let's see, there's that one more piece. Our cost per item was $5. So our profit is going to be this formula, 10,000 over 200 plus x times x minus 5 times x. Okay, so that's our profit. Correct. Yeah, so this was the cost per item to produce. Yeah, so when they talk about cost, they're talking about manufacturing costs, not the cost to the consumer. Okay. This is best to rewrite as a single fraction. So this we really want to write as 10,000x over 200 plus x minus 5x. And the reason we created this is the next part of the problem is we want to maximize our profit. So how do we maximize the function? Do what? It's not that we choose a really big number. Do what? Take the derivative. Right? Every time we want to maximize a function, we're going to find critical points. So let's reset here. Our profit function is 10,000x 200 plus x minus 5x. We're going to calculate this derivative. I have to use the quotient rule. 200 plus x low d high, so that's times 10,000, minus high 10,000x d low, which is 1, over low 200 plus x squared, and then we have to remember the minus 5. So when I multiply this out, I'm going to get 10,000 times 200, which is 2 million. I'm lazy, so that's 2 times 10 to the 6th. Plus 10,000x, and notice minus 10,000x. Those cancel. And so I get over 200 plus x squared minus 5. And we care when that's equal 0. So I'm going to add the 5 to the other side and cross multiply. So when I solve this, I get 2 times 10 to the 6th equals 5 times 200 plus x squared. Divide both sides by 5. Now I get 4 times 10 to the 5th, 400,000, is equal to 200 plus x squared. Take the square to both sides. And so I get 200 plus x equals plus or minus whatever that is. So can someone quickly, or look on the paper, there was a number that was 600 something?
So x equals 432.455.
632.455. Okay, and so I'm going to have, when I solve for x, I need to subtract 200.
It's 432.
The final answer is 432, right?
After you do 200 out.
After I take the 200 out.
Yeah.
I haven't taken 200 out yet.
Oh, right.
So when I subtract 200, I have 2 possible answers. X equals 632.455 minus 200, which is 432.455, or x equals negative 632.455 minus 200, which is negative 832, which is not physical. So we want to sell 432 items. Yeah? That was the square root of this number, 4 times 10 to the 5th.
We lose points if we didn't show like three not possible answers. If we just went right to 432, we didn't have it.
Probably not. Okay. So that's the number of items we want to sell. So technically it would be, if we were really careful, we would have to check 432 and 433 and compare them. But we're just going to use the fractional number of items. And when you plug that into the price formula, the price to charge what did I write down there? Is 12 something?
15.
Is 1581? So we would want to set our price at $15.81. Now, maybe there's some economic reasons that people would shift that to $15.99 or whatever it is, but so that's what I would set my target price at. Okay.
So we plugged in the 432 into the X.
Right. So I plugged 432.455 into the price formula to figure out what the price was. Thanks for clarifying. Okay.
So what does that X value give us? That's the number of items we have to sell?
Yeah, so this is the number of items to sell that maximizes profit. Okay. So problem 5 was a graph of a derivative. And it was to find out where the original function, or figure out what the graph of the original function would look like. Our time has gone by a lot faster than I expected. So is this one you want me to spend time on? So let's not do this one. Okay? All right, but the solution is available written out. All right, so how do you want to spend our last half hour? Are there some, yes?
I guess just going over the integral step, because we did a lot with it, but I don't know how many variables and what's different.
Say that again.
The integrals, we did a bunch of different stuff with it.
Okay, so I'm looking at the review guide that's since exam 3. All right. So for example, you might be expected to write down the Riemann sum. For an integral, like the integral from 2 to 5 of 1 over x dx. Okay, so if I'm going to do that, there are 3 steps. You need to calculate delta x, you need to calculate xk, and then you need to use f of xk in the formula. Sum k goes from 1 to n, f of xk times delta x. So that's how these always work. This is the right-hand sum rule. And the only difference for the left-hand rule is you use xk minus 1. But most of the time, and Might as well just plan on it, a right-hand rule for the problem. Okay? So delta x is always b minus a over n. It's the ending point minus the starting point, which is 3 over n. My xk is always my starting point. Here it's 2 plus k times delta x. So here we get 2 plus 3 over n times k, 3k over n. This is the formula I'm going to use in the function. So my function is 1 over x. So we're going to do 1 over xk. 1 over 2 plus 3k over n. This is the formula I'm going to use in the Riemann sum. And so my Riemann sum for this integral is the sum k goes from 1 to n, 1 over 2 plus 3k over n times delta x, which is 3 over n. That's the Riemann sum that approximates the integral. Okay, so you would be expected to be able to do that. Secondly, on the question it asked you, can we find a formula for this? Using our elementary sums. So remember what those were? We knew how to do sum. K goes from 1 to n of a constant was c times n. We had the sum k goes from 1 to n of k. That was n times n plus 1 over 2.
Wouldn't we have to multiply that out before we do anything like that?
Like multiply out the 3 over n?
Yeah.
You could, or you could think of that as a constant multiple and it just comes in front of the sum. So what do you think? Can we do anything with this sum? The answer is no, because it's inside of a fraction. Right? Linearity only lets me split pluses and minuses, not division. So I'm not going to be able to split this up. So we have no rule for what to do at this point.
So Riemann sum is just figuring out that formula.
Correct. The Riemann sum, exactly. This is the answer. This is the Riemann sum. The value of the Riemann sum is if we could find a formula that only involved n. But we can't do that for this. Okay, so problem 2, we're looking at an integral -2 to 2 of 1 plus x squared dx. Okay, so the same basic idea, delta x is 2 minus -2 over n, that's 4 over n. It's the total width divided by n. Our xk is always the starting point, -2 plus 4k over n. And our Riemann sum is k starts at 1 and goes to n, of the formula 1 plus this squared, -2 plus 4k over n squared. Here is my f of xk times 4 over n. Okay? That is the Riemann sum. And that's all it's asking for. Okay? Now the second question here is, would it be possible to find a formula for this one? So you're saying no, why? It's not a fraction. Right? In that other one, it was 1 over, that's where the k was.
The 4n will go into the function.
So the thing is, if I expand this, right, with FOIL, you're going to have a sum of something with no k's plus a sum of something times k plus a sum of something times k squared. And we have rules for all those. So in this example, after you expand it, we could use linearity. The problem with the fraction is there's no linearity involved with division. but there is if I expand this. So this one we would be able to, although I don't think I ask you to. Okay? Let's see. Problem 3 is to write down a Riemann sum and find its value. So let's just do problem 4 where the Riemann sum's already written out for us. We're taking a limit as n goes to infinity of a sum, k goes from 1 to n, of 3 plus 4k squared over n squared times 2 over n. Okay. So the idea here is it's already been written as a sum. All I want to do is find the value of the sum. So let's multiply this out. So I get 6 over n plus 8k squared over n cubed. Linearity lets me split this into 2 sums, so I get a sum of the constant plus the constant 8 over n cubed sum of k squared. So the sum of a constant is the constant times n. 8k squared would be given to you, and that is n times n plus 1 times 2n plus 1 over 6. Yes?
So this was like the second to last problem on our test?
Correct.
Where you just asked us to evaluate this and you had the limit.
Exactly. I gave you a Riemann sum that maybe had already been simplified to some extent. Okay? So this is actually the value of the Riemann sum. It's a little easier if we simplify it slightly. The n's cancel, and that n cancels, so that I get a value of 6 plus 8 times n plus 1, 2n plus 1 over 6n squared. That's the value of the Riemann sum. The limit of the sum, I'm going to let n go to infinity. So 6 plus 8n plus 1 times 2n plus 1 over 6n squared. Earlier this morning we talked about it's really just the highest powers that matter. So if I multiply out the top, notice I'm going to get 2n squared times 8. So I'm going to get 6 plus 16n squared plus smaller stuff over 6n squared. And the only thing that's going to matter in the limit, when you factor out the n squared, it's just the leading terms. And so it's going to be 16 over 6, whatever that is, 8/3. So we'll get 6 plus 8/3, that's 8.66. Repeating forever. Okay. And I did push through that limit a little faster rather than spend all the time on it. Okay.
So the 8.66, that's the value of the limit, and then the 6.8 times n plus 1, that's the value of the sum.
So this is the value of the sum. This is the limit of the sum. And that would be, this would be the value of an integral. This is the approximation of the integral. Okay, so that's that first section from the review. Let's see, the next little section is about what an integral means. Okay, so let's see. So the first one is this understanding properties. Integral from 1 to 3 of f of x is 8. Integral from 1 to 6 of f of x is 5. And we're supposed to find an integral from 3 to 6 of f of x plus 3x. Okay? So this problem involves multiple steps. There are two key things that I'm practicing here. I'm actually applying both linearity and splitting. So what is linearity? We're splitting the formula. So linearity lets me write this as integral from 3 to 6 of f of x plus 3 integrals 3 to 6 of x. That's linearity. Splitting is where I'm going to use these two integrals to figure out this integral.
That's where you have to go from like 6 to 0 to.
Well, I don't need to go to 0 here. So here, what do I have? I've got a function 1, 3, and 6. From 1 to 3, I know that integral is 8. From 1 to 6, I know that integral is 5. And so the integral from 1 to 6, the whole integral, minus the integral from 1 to 3, is the integral from 3 to 6. This is where I end, where I start. From 3 to 6. And so this first part of the integral is going to be 5 minus 8. Then how am I going to do the second piece? How would I integrate x? What? Don't think too hard. We have a really easy way of doing these now. Yeah, we're just going to use the rule. So which rule? I can't just plug it into something yet. I need the antiderivative. So it's going to be 3 times the value of the antiderivative. Right? So what allows me to do that? Fundamental theorem of calculus says if I know an antiderivative, I can find the value of the integral. And so I'm going to plug in 6 and 3 into the antiderivative. So I get negative 3. Let's see what I get. 36 halves is 18 minus 9 halves. So it's negative 3 plus 3 times 18 minus 9 halves, whatever that is, but I don't want to waste our time.
So that's when you did the n minus the start and times 3.
Antiderivative end minus start times the 3 from the constant multiple. Or you could have left the constant 3 in there, and then the antiderivative would have been 3 halves x squared. So you didn't have to bring the 3 out if you didn't want to.
So the fundamental theorem of calculus is where you take that, you do the antiderivative, and then that's n minus start.
Correct. That's the fundamental theorem of calculus.
And if it's like something that's not x, you can just change it to x, right?
Like if the letter's something different?
Yeah.
you think the same way as if it was x. You probably shouldn't change it, but the letter does not matter. Okay. The second problem, we have a formula for a velocity. Measured in meters per second, t is time measured in seconds. We have a position at time 0 is 20. Measured in meters. And our job is to find the position after 5 seconds. So how would I go about finding the position after 5 seconds? Actually, there are 2 ways we could do it. What were we saying? So one strategy is find an antiderivative. And then there's a plus c in it, and what would you have to do? You'd find c to make this work, and then you just plug 5 in. There's another way. By the way, that happens to be easier as I'm thinking about it now. The other way is that s of 5 is always equal to where you start plus how much you change. And the integral of velocity gives you the change in position. And this is one of the things I've really tried to stress the last 4 weeks here of class, that the integral of a rate is the total change. But in this example, yeah, I think finding an antiderivative is actually probably the better strategy. So what would I do? I'd multiply it all out. 4t, FOIL that out, t squared minus 7t plus 10. So my velocity is 4t cubed minus 28t squared plus 40t. And you find an antiderivative. 4t cubed gives me t to the 4th. 28t squared gives me 28 thirds t cubed. 40t antiderivative gives me 20t squared plus a constant. And when t equals 0, I should get 20, and this is convenient because t equals 0 makes everything go away but the c. And so then I plug 5 into that formula. S of 0 is 0 minus 0 plus 0 plus c. That should equal 20. And so we get c equals 20. And then I plug it in. And again, I don't think that part of the problem is probably worth us spending any time on. But don't forget that important point. Yes?
How many questions have you done with that? Do you know yet?
I do not know yet. You should expect it to be about 1 2/3 of an exam from last time. It's about that size. Yes? I honestly can't guarantee that now because of just the time constraints. I wish I could. I will try, but writing the test has to take priority, and I'm not going to have any time today to do that or the solutions. Correct. Yeah, so the problems 4, 5, and 6 on that second or the third section, all of those are about finding antiderivatives. So, and the key there is remember to say plus c because I'm finding the family of all possible antiderivatives. Okay.
Since you have in this session today, maybe you can just put the ones that I didn't go over in my class.
Yeah, I understand. That's where I would put my priority, but again, I can't guarantee I'm going to have time to get the exams written and have this posted. Okay. Let's see. Might as well use the last 5 minutes. Which one should I write up and it'll be on the video? Let's see, what have we not done? That's going to be straightforward. Let's do that one. Okay, so this is on the second page of this problem. We're defining, in part 1, we're defining a function, and then in part 2, we're doing something almost the same, right? It's the same integral, but with different limits, okay? And so the reason I wanted to pick this one out is I wanted to point out that this is really the fundamental theorem of calculus. That there is a function. This thing is called an accumulation function, where you integrate from a number, and it doesn't matter which number it is, to your variable of a formula. And the fundamental theorem of calculus is what says this thing has a derivative that's equal to the rate, x squared e to the x. So I'm plugging x into the integrand function. That's what the fundamental theorem of calculus really is all about. And once I have these functions, this is an antiderivative. And since this is an antiderivative, every definite integral can be written as a difference. And so this question is saying, what's the derivative of this? It's equal to x squared e to the x. Done. Bang. I'm done. It's all over. Like, it's super fast. This problem looks the same, but it's slightly different. And the reason it's slightly different is I've got strange things. It's not a number, and it's not just x. So what I do is I say, all right, I'm going to take a derivative. Just a little bit, yep. I'm going to take a derivative of this integral, which is how much the antiderivative changed. Because every integral can be written as the change in the antiderivative. Now, when I take the derivative, I'm going to need to use the chain rule. And so we're going to get a prime at x squared times 2x minus a prime at x, no chain rule involved. This is my a prime. I'm going to plug x squared into this x and this x. And so I get x squared squared e to the x squared times 2x. This is a prime of x squared. Okay. And I'm going to subtract a prime of x, x squared e to the x. So what's x squared squared? X to the 4th, so I'll get 2x to the 5th e to the x squared minus x squared e to the x.
So for this type of problem, in order to do that one, we have to do this first, figure out the general.
Correct. So the thing is, you have to have an accumulation function and know its derivative before I go and I calculate the chain rule on the second piece. And then I plug the x squared into the rate, and then I plug x into the rate. And so I think that is probably the last one we'll do. Okay. I will post a link to the video on Canvas, and you can go back and watch it.